Welcome to our read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is section 4.3, and we're going to just begin it right here. We're going to be talking about groups. What is a group? It's a set with operation on it, such as addition, that follows certain rules or properties. For instance, let's take mod 5 arithmetic. So these are fiber chunks right here, and we can add them together and we get other fiber chunks. So there's like 5 things we can add with each other, and there's a nice addition that happens right here as we do so. And notice 1 plus 2 is 3. So no matter what we add, like 3 plus 4, we get something back here in the same set. So it's a closed binary operation. Also realize that in every single row there's a 0, and in every single column there's a 0. That means that if I take that everything has an inverse with respect to this operation, like 4 plus 1 is 0, or 3 plus 2 is 0. Okay, so there's a unique additive inverse. There's exactly 1. Okay, there's also something called associativity. Now, if we recall, associativity looks something like this. Like we can move parentheses around, and we can regroup things. Now, this actually is given to us for free if we took it from a group, if we preserved an operation from a bigger group, like, or a bigger set with that operation, such as the integers. And if we preserve it down, the associativity naturally transfers down. So since this is just a merge of z with the addition and z preserved, then this is associative as well. So we get that one for free here. And then just looking at the table, we just check that everything has an inverse and the operation is closed. And then we already given associativity for free. Then we know, then we call this a group. So see how there's, so there's different things here. So it needs to have inverses. The operation needs to be closed, needs to be associative. And of course, there needs to be an identity. You can't really have the inverses to go to the identity without the identity itself. So with these conditions, we have a group. Okay, so that's what a group is. And this is just a definition in general. So we can verify that this structure right here defines a group for the same reason. We have zeros in every single column and row, and it's closed because we see everything there. We know the operation was transferred from the integers in a nice merge that preserved it. So therefore associativity was transferred. And there's an identity element, 0. Notice that this, 0 plus everything is just itself and both ways. And so we get that it is an identity. And so that is a little description of groups. Okay, let's take a look at multiplicative groups as well. So, well, first of all, let's look at this set, z mod 6z, and think of it with multiplication. Does it form a group? Well, what's the identity with respect to multiplication? It's 1. And then we look, does every row and column have a 1? This one doesn't, and that one doesn't. In fact, this one doesn't even, and that one doesn't even. There's some rows and columns without 1s. So we don't have inverses everywhere. So this can't be a group. However, what if we were to take only some of the elements, the ones that actually had 1s in them? Like this one has 1s, that column, and so like this one has 1. So there's only 2 columns and their corresponding rows that have 1s in them. What if we just restrict ourselves to those and take out all the other elements? We actually get a table of 4 things then, because we've eliminated those rows and columns. And it actually, notice, it is a group. 1s are in each thing. It's closed in of itself. And it's associative, since the operation of multiplication in integers was associative and it was preserved in the merge. This little symbol right here, this little cross, that just simply means that we took z mod 6z, so we took mod 6 arithmetic, and we took away everything that didn't have an inverse. So that's all that means. So we can read this as z mod 6z cross. Just means we took away all the mod 6 stuff that doesn't have inverses. Then we actually have a group. This is a multiplication group. So here we can do the same thing, just throw out everything that doesn't have inverses. And notice, so we just have things with has rows and columns with 1. And if we do that, actually, it turns out that we have something that's closed. So every time, it's just, if you throw out everything that doesn't have 1s in it, notice that it's what we get is closed. Closed meaning that if we take 5 times 7, we still get something in these numbers right here. So we actually get a group. So we throw out certain elements and we get a group, and with multiplication within a mod. And here's a little statement here. So which basically shows that this is a group, meaning if we throw things out like that in general, we get a group. Namely, like, in fact, if you look at this proof here, a times b, we're checking to see if a times b has an inverse. That's the same thing as saying that a times b, so a product, actually ends up being in this list, because it's a list of things that actually have inverses. And we'll conclude this little read along with that. Thanks for watching.